Hey everyone, and welcome back to the Foundry by Forge College. I'm your host, and today we're rolling up our sleeves, grabbing our drafting pens, and stepping right into the role of lead engineers. Now, if you're a developer getting into the weeds of Web 3, you already know that before we write a single line of code, we absolutely need a flawless architectural blueprint. Because if we don't have one, well, things tend to catch on fire, mathematically speaking. So today we're laying out the exact security goals and project overview for your capstone implementing secure blockchain structures. Think of this explainer as your master schematic. We're going to figure out exactly how cryptographic hashes, Merkle trees, and digital signatures all snap together to form an incredibly unbreakable machine.
So, here's our engineering agenda for today. First, welcome to the capstone. Second, the sealed ledger metaphor. Third, cryptographic security mechanics. Fourth, building a secure block. And finally, testing and next steps. Let's dive right in.
All right, Section 1. Welcome to the capstone, where we set our strict security boundaries.
Now, if you caught our previous explainer on authenticity and non-repudiation, you'll probably remember one massive concrete insight, and that is a digital signature only guarantees that a specific private key endorsed an exact sequence of bytes. That's literally it. It doesn't just magically secure an entire system if your inputs are a total mess. So we're shifting our focus today. We're moving away from looking at signatures in isolation, and instead, we're defining our overall security architecture. We want to see how hashes, trees, and signatures all interlock and operate together as one unified engine.
Moving on to Section 2, the sealed ledger metaphor. This is where we explore the physical mechanics of trust.
The easiest way to wrap your head around complex cryptography is to picture a physical object. So imagine a physical book, a sequence of sealed ledger pages. To stop someone from tampering with a page in that book, you really need three things. You need a unique fingerprint for the page itself, an index of fingerprints for every single entry, and a heavy, tamper-proof wax seal stamped right on it by the author. Now translate that messy, hot wax reality over to our pristine mathematical equivalents. That page fingerprint, that's our cryptographic hash. The fingerprint index, that's our Merkle tree, and that authoritative wax seal is our digital signature. Basically, the hashes handle the integrity, the signatures handle the authorship, and the best part is nobody burns their fingers.
Which brings us to a really crucial concept, canonicalization. Just imagine trying to stamp a physical wax seal onto a piece of paper, but the ink on the page is magically sliding around and changing shape. It'd be a total disaster, right? The seal wouldn't mean anything. Well, in our technical reality, canonicalization means freezing that ink. It's the absolute enforcement of an exact, standardized byte sequence before you apply your digital signature. If you don't rigidly format those headers, attackers can and will exploit that ambiguity to launch replay attacks.
Okay, Section 3, cryptographic security mechanics. Let's pop the hood and look at the gears of this machine.
Let's break down the three core properties our cryptographic hash, our digital page fingerprint, absolutely must possess. First up is preimage resistance. This simply means you can't reverse the digest. You can't unbake the cake to figure out what the original ingredients were. Second is second-preimage resistance. This means if I hand you an input and its resulting hash, you can't subtly tweak that input to somehow produce that exact same hash again. And third, collision resistance. It has to be statistically impossible for an attacker to find any two completely distinct inputs that magically result in the identical hash. These three properties are the bedrock. They are exactly what stops an attacker from forging or tampering with our ledger data.
Now, look at this engineering spec sheet. The crucial point here is how we map these primitives to actual real-world threats. Your cryptographic hash defends against tampering, sure, but you have to actively make decisions on your algorithm and your input encoding. Your Merkle tree defends against fake entries, but only if you strictly document your leaf pools and pairing order. And your digital signature defends against forgery, provided you lock down that canonical serialization we just talked about. You see, security isn't just about throwing the right tools at a problem. It's about making and thoroughly documenting the exact mechanistic decisions of how those tools are applied.
Moving to Section 4, building a secure block. Let's walk through this step-by-step construction.
I want you to imagine you're a master inventor assembling a flawless mechanical device. Here is our chronological assembly line. Step 1, we compute the transaction IDs. We're essentially hashing our raw data into leaves. Step 2, we build the Merkle tree by pairing those hashes together over and over again until we reach one single unifying root. Step 3, we construct the header. We take that Merkle root and organize our fields in a strict canonical byte order. And finally, Step 4, we apply our digital signature, sealing that canonical header with our private key. It's a beautiful process, isn't it?
But remember what we said earlier. Ambiguity is the enemy of security. While you're assembling this block, you must make firm, documented decisions, like what is your leaf hashing strategy? Are you using domain separators so a leaf hash can never be confused with a parent hash? Does your tree pair left to right? What happens if you have an odd number of leaves? Do you duplicate the last one or do you promote it? And what is the exact canonical byte order for those headers? If you just leave these up to chance, your proofs won't be deterministic. And if they aren't deterministic, your entire machine just falls apart.
And finally, Section 5, testing and next steps. Because now, it's time to prove the blueprint actually works.
Let's take a look at the brilliant dynamic between the prover and the verifier. On one side, the prover supplies a specific transaction, the necessary sibling hashes, and the expected Merkle root. On the other side, the verifier doesn't just blindly trust the prover. No, the verifier actually recalculates the root from those pieces and checks the signature entirely independently. This separation of duties is exactly what allows light clients to exist on a network. A light client can verify that a transaction is secure without having to download the entire, massive history of the blockchain. It's elegant, it's lightweight, and it is highly secure.
So before you run off and start writing your implementation, you need a strict checklist. Here are the acceptance criteria for your capstone. You have to verify that domain separators are applied to your leaves. Your Merkle proofs must flawlessly reconstruct the exact root. Your signature verification absolutely must reject any altered headers. You also need to run negative tests, and by that I mean intentionally tampering with a single byte just to make sure the system actually catches the error. And lastly, you must prepare deterministic test vectors so you can properly validate your hash functions in the upcoming coding phase.
Before we wrap up, I want to leave you with a core piece of wisdom. Honestly, every junior developer should have this tattooed on their brain. Canonicalization matters as much as cryptographic strength. Ambiguous byte representations defeat signatures. Think about it. The most mathematically complex, unbreakable cryptography in the whole world is completely, utterly useless if the input data it's supposed to protect is just a disorganized, ambiguous mess.
So here's a provocative little thought experiment to mentally test your design right now. If you changed a single byte in a transaction today, would it escape detection in your blueprint? If your answer is yes, well, you need to go back and revisit your canonicalization and hashing rules. Thank you so much for joining me on this explainer. If you want to dive deeper, put these blueprints into actual practice, and master the rest of your Web3 engineering journey, you've got to head over to forge.college to explore this subject and a whole lot more. Until next time, keep building securely.